Now we'll turn to Udayan Singh. We discovered over the coffee break that we have a lot in common, at least in the space of eclectic research interests. Udayan is from the University of Virginia, but in addition to the work he'll be describing today, he's done a lot in the space of carbon removal and the full spectrum of climate responses, also thinking about the giant models used for economic, land, and energy modeling towards climate resilient responses.
Thank you for the introduction. As you said, I'm Udayan Singh. I'm a graduate student at the University of Virginia, and I've broadly looked at decarbonization work, reducing CO2 emissions from our electricity sector generation. But we have recently gotten funded by our university's Environmental Resilience Institute, and so I'll like to briefly talk about why decarbonization alone is not enough, why we need to think beyond that spectrum of just reducing CO2 emissions, and also what are some of the features we want to talk about in the context of a resilient energy or a resilient electricity sector. So the first thing, of course, when we think in terms of energy and climate change simultaneously is reducing CO2 emissions, because energy sector is the largest CO2 emitter. So if you look at some of the strategies that have been proposed, this for example, is the Obama administration mid-century strategy for decarbonization, and it aims at 80% reduction of CO2 emissions between 2005 and 2050. You'll see that a lot of these portfolios come from decarbonizing energy supply. And so almost 60% of this emission reduction in the Obama administration plan was supposed to be through decarbonizing the energy sector. But as we know already, through multiple hurricanes and multiple extreme weather events, decarbonization is not enough. For example, the figure you see on the left, Puerto Rico was already gearing up towards the renewable sector, renewable grid, but at the same time, just the way the geography is arranged, extreme weather, some areas are particularly prone to extreme weather events. Similarly, on the right, the Hurricane Harvey, and these impacts of extreme weather on the electricity sector are well known. And so it's not just these extreme weather events and the outages they are causing, but also that the impacts of these outages on our society will be even more. So in the future, when we are thinking in terms of electrical vehicles, as well as digital economy and stuff like this, the importance of electricity sector on our lives will also grow. And therefore, we must think about a resilient and robust electricity sector. So in that context, we looked at the literature and what sort of features are talked about for resilience, even broadly beyond electricity. And we came up with 4 of these features which we want to model. 2 of these we have already tried to model preliminarily, the diversity and redundancy, and 2 we are conceptually thinking about and will hopefully model throughout this year, decentralization and flexibility. And I'll talk about these shortly. So the first is diversity of generation mix. A diverse electricity mix is a more resilient mix in principle, because different energy systems respond differently to a particular extreme weather event. So for example, if your electricity is heavily reliant on hydropower, of course a drought will affect your electricity mix much more. Similarly, if you have a lot of flooding and hurricanes, you might have to shut down your nuclear power plants prematurely because of safety reasons. But if you have a diverse electricity sector, that would mean that even if one sort of energy mix you cannot rely upon, you can hopefully use other sources to get your electricity during that time. And this is not something we have discussed. Even the other literature, such as the Global Energy Assessment, has looked at Shannon-Wheeler index, that is a metric of diversity, as a proxy towards resilience. What we want to do is discuss this at a more localized scale, because resilience is a very, very localized concept, obviously. And so what we did was, I mentioned Obama administration's mid-century strategy for decarbonization, which is aimed at reducing CO2 emissions. We wanted to see how does that impact the diversity of the electricity mix. And so we used the Global Change Assessment Model, which is an integrated assessment model. And what we found out was, while of course these decarbonization plans aim at reducing CO2 emissions, at the same time, the co-benefit is that the diversity of the electricity mix also increases, which is shown by the darkening of these colors of the Shannon-Wheeler index throughout the US states. And so therefore, often we think of sustainability and resilience as competing objectives, but as we show here, there might be often co-benefits at times as well. The second, but also at the same time, when I said about mapping, we have mapped out the diversity and other characteristics of the future grid as it would look like under different scenarios. And this is really important because we know which parts of the country are particularly vulnerable to large-scale outages, and which you see on the right. So the map on the right shows which states are particularly more vulnerable to outages due to extreme weather events. And so basically states like California, Texas, coastal states, New York are more vulnerable, and you want to build a more diverse grid in those states. The second component I'd like to talk about is redundancy. What does redundancy mean in the concept of resilience? Is that even if one part of your infrastructure fails, you have some standby or adaptive capacity which you could use to have some resilience in your system. Now, this is really important because if you look at where the power infrastructure in the US is, it's mostly towards the coast, and that is hardly surprising since most of our population is towards the coast. And so if there is extremely high probability of extreme weather events, you want to have some standby capacity inland such that you have a resilient electricity infrastructure. And so using the NOAA data for the sea level rise, how much that would impact the land vulnerability, and we know which power plants and substations exist in those regions. And so we modeled what sea level rise would affect what number of vulnerable electrical facilities. And as expected, of course, a higher sea level rise would mean a lot of our electrical facilities in multiple cities become vulnerable. That could affect the electricity supply. So right now we have mapped out the number of electrical facilities that would become vulnerable. But in the future, what we want to do is using this data to find out if these are the number of power plants or substations that would shut down, what is the amount of standby capacity you would need such that you could get robust power supply even in extreme weather events. So this is the work we have already completed, but what we are looking at right now is decentralizing and flexibility as two more features. So what I mean by decentralization is similar to redundancy. If instead of one big power plant model, which we have right now, we build 5 smaller power plants so that even if one gets shut down, you can still get electricity for the rest 80% of your grid. Now, why have we not been doing that so far is because it makes economic sense to build larger power plants. As you see in this figure, larger power plants brings in more economies of scale, and therefore the capital cost per unit power is smaller for larger power plants. But at the same time, there is economic value to having resilience in our system, and that is something we are trying to model right now. It's difficult to put prices on subjective things, and we are taking the help of a commerce professor in doing so. And then final feature I want to talk about is, of course, flexibility. What I mean by flexibility is our outdated coal power plants, for example, they could only use coal, and there was also a susceptibility to water supply. So if you don't have water to run those power plants, cooling water, those power plants will shut down. But the power plant of the future would probably be able to use 2 or 3 fuels if one particular fuel source was not available. So a lot of attention is being given to bioenergy and stuff like this. But suppose you have a biomass gasification plant and you don't obtain biomass 1 year due to some reason, you could use some waste materials to gasify and produce electricity. And so thinking about these sort of technological alternatives to bring in flexibility to our system. And so my objective in this project is, of course, as an engineer, I think I am skilled to model a power plant level techno-economic assessment. At the same time, I'm using the global change assessment model, which is a macroeconomic integrated assessment model, and that model is developed by the Pacific Northwest National Laboratory, and they are very good at modeling global and national scale level features of the energy system. And so integrating some things at the plant level and the national or global level can hopefully help us not only get information about these 2 levels, but also at something, if we could upscale our analysis and they could downscale their analysis a bit, we could also have a very, very useful information set about the regional or grid level, which is really important in context of electricity sector resilience. And so that is the work we are looking to do right now. Thank you so much.
Great, and we will take a question. I'll throw one out there. IAMs are wonderful state-of-the-art tools, but they have real limits in terms of the phenomenal complexity they're trying to represent. How well do you think they are working in this more straightforward application of electricity systems as compared to some of the places where it's been harder to tease out the trends?
So one of the concepts we are trying to use in the IAMs is, of course, we are using a subnational IAM. That is, most IAMs look at different countries at particular units within their calculations. We are using the USA-centric version of the global change assessment model, which can hopefully help us give particular examples. So there is detailed expansion about capacity, dispatch, and stuff like that inbuilt into this version of GCAM, which hopefully, but of course, we are trying to supplement that using our own energy systems model, and which can hopefully give us information about how power plants operate. And that is where the integration is, because a lot of times the criticism they face is being too broad, and the criticism we as engineers face is not being broad enough, not being contextual enough. And so that is where the merger, we are trying to find out the sweet spot between large scale and top down, bottom up kind of thing.
That's great. Thank you so much.